In our previous example, we were experiencing a situation where in every iteration of the loop, two read requests, one write request, and the corresponding response were performed at every cycle. In addition to that, each read and write operation encountered at every loop iteration were possibly causing a stall in the computation since it needed to wait for the memory controller to complete the corresponding operation, with an heavy impact on the corresponding performance. In order to overcome these limitations, we can optimize data transfer by using memory burst. The idea is to combine a single memory transaction that accesses consecutive memory elements into one or more larger transactions. As the Excel allows to request up to 4 KB of data, Vivado HLS can automatically infer burst memory transfer when we read and write data in consecutive memory elements within a pipeline loop. However, loop pipelining will be presented in the dedicated class. Alternatively, we can explicitly make use of the memcopy calls and specify the number of memory elements that we want to read from the external memory or write to the external memory. In order to follow this approach, we need to leverage on the cheap memory resources provided by the FPGA. In particular, Xilinx FPGA provide BRAM resources, each capable of storing up to 18K bits. Xilinx FPGAs contain several BRAMs, and depending on the target device, it is possible to store up to 10 MB of data locally. Furthermore, each BRAM provides two memory ports for concurrent and fast read-write operations. In order to use such resources, we simply need to declare local arrays within our kernel function, which will be automatically mapped to BRAM resources. Overall, in order to exploit memory burst, we can decouple the function in three sections. First, copy several memory elements from the DDR to the local BRAM exploiting memory burst. Second, to the actual computation accessing data to the local BRAM. Third, copy back the results from the local BRAM to the DDR exploiting memory bursts. This is the new version of our kernel function. We can see that three local arrays have been declared to store both the input and data output. First, we use memcopy calls to read data in burst mode. Then, we do the actual computation, reading and writing data to the local arrays, and finally, we write back the results with memcopy from the local arrays to the external DDR. Looking at the new performance estimation, we can notice that the number of cycles per loop iteration reduced from 23 to 10, and the overall latency more than halved compared to the initial design. Notice, however, that the HLS synthesis report do not estimate memory transfer stalls to the external DDR memory. Actually, with this new design, we can expect more than a 2x speed up against the initial design. And looking at the HLS schedule, we can see that the latency of the summation loop is now mostly due to the floating point sum operation, while just two read and write memory requests are performed in burst mode. And three corresponding loops are created to handle the copy of multiple data elements across the DDR and the local memories. And finally, when attempting to use memory burst, it's important to verify that Vivado HLS applied it. To do so, we can simply double-check the Vivado HLS logs as it's reported here.